So now we're going to look at classifier metrics, such as accuracy, which everyone knows about, but also recall, precision, F1, and importantly, rock curves. Okay, so we're going to use the mowers database and then also the universal bank database here. So the universal bank database, you remember that the goal was to figure out whether or not we're going to get a personal loan. Okay, so the very first thing to look at is whether or not just simple attributes separate the classes. Okay, so here's a bunch of utility code. But what it's going to do here is for mowers, it's going to plot income and lot size versus ownership. And then for the second one, universal bank, it's going to plot whether or not we got a loan based on income. So let's see what happens. Okay, so here for the riding lawnmower, you see that income and lot size separate the classes fairly well. Basically, if you have a small lot size and you have low income, then you're not going to be an owner, otherwise you are going to be an owner. And again, annual income and average credit card spend also separate, right? So basically, if you have a high income, you're going to be able to afford a personal loan, otherwise you're not. So that immediately gives us some understanding of whether or not we can use a classifier, a decision tree classifier, who's going to make exactly these splits. Okay? Okay, now we're going to look at owner, okay, which is just a little data set here based on the riding mower data set, which just tells us what the probability of being an owner or non-owner is. And then we're going to use different cutoffs to see what our confusion matrix is. So if we have a cutoff of 0.5, here's what the results are. If we have a cutoff of 0.25, here are what the results are. And so you can see how you can benefit and penalize certain things, right? So based on the cutoff, you get different results, of course, and you can decide which one you want to be a higher accuracy. And so sometimes people think, well, I'm just always going to use the cutoff of 0.5. But when your classes are asymmetric, like in a medical diagnosis case, where saying that someone is free of a disease is very dangerous, if they have the disease, you may want to use a different cutoff. Okay, now we're going to look at rock curves, and we're going to look at this lift example. Okay, and so this is the probability that is assigned, and then this is the actual probability. So again, what we do here is we use various cutoffs to determine different performances. So here we have our rock curve, sensitivity minus 1 minus specificity. Remember, if it's the diagonal, it's random, and if it's going straight up to 1 and then straight over, then that means it's perfect. And then we can choose, right, what we want the performance for our algorithm to be, right? So if we want perfect sensitivity, then the best specificity that we can get is down here, right? And likewise the reverse. Right? That's how we read the graph. And then we calculate the area under the curve, which is 0.9375. So remember, if it's 1, it's perfect. If it's 0.5, it's basically random. Okay, now we can look at precision and recall. And this is all random things. So this is a beautiful graph. Okay, so here we have F1, which is a combination of precision and recall. And you can see that it's maximized at around between 0.5, 0.6, although it's flat for a pretty long range, which is pretty cool. Okay, and then you see that precision and recall trade off, as you would expect, right? Recall means that we're getting everything. Precision means we're only getting the good things. So that's the basic introduction to classification metrics, and now we're going to go on to clustering.